This is our presentation on the real-world applications of the various engineering disciplines that we learn about. I'm Luca.
I'm Drago. I'm Grafton.
I'm Edward.
I'm Nate.
So the first day we had this program, our topic was about how material sciences could essentially be used to power our society in a renewable way.
So what we first did was we made solar cells. They're made of two glass slides and silicon layers put on top of each other. They are low maintenance and used in most parts of the world. They're made of clean energy. When you put them on top of each other, they create an electrical field, and if the sun is shining down on them, while you have two metallic sides, they create a flow of electricity.
So we actually made two solar cells ourselves. The first step that we used was we added titanium oxide onto a conductive piece of glass. And this basically made it so that photons that were UV light could be absorbed by the solar cell as well, which would essentially generate more electricity because more light particles would hit the solar cell and would get absorbed. The next part was we added dye, which expanded the absorption spectrum of just visible light, which generated or helped generate more electricity as well. Then we added an electrolyte solution to increase the conductivity of the solar cell. And then we added a second piece of conductive glass on top to finish the circuit and the solar cell. And in total, we made two solar cells, and we were able to generate about 250 millivolts of electricity, which is roughly 25% the average efficiency of a normal solar cell, which isn't that bad.
So now we want to look at solar energy and material science and engineering in a real-world application. So Rutgers actually has an agrivoltaics program where they connect with local farms to build solar panels on those farms, which allows those farms to increase their energy independency and therefore increase their revenue and income. And material science and engineering can be utilized in this program to develop more efficient resources that are cheaper and therefore increase the farm's energy independency and revenue even further. We actually have a quote from a senior associate director of the program. "I'm confident that we can utilize this new technology to not only generate clean energy, but also improve farm viability and sustainability."
On the second day, we did chemical engineering, and the prompt was how can programming and data visualization help us understand and communicate about extreme environments. So we used Python to analyze three different equations of states to calculate pressure, which were the ideal gas law, the van der Waals equation, and the Pang-Robinson equation. And we used the equation on the board right now is the Pang-Robinson equation. We used Python to graph these different equations and compare them with the NIST data points and see which ones were the most accurate. And we found that the Pang-Robinson equation was the most accurate, but it was also the most complex. And that contrasted with the ideal gas law, which was the least complex, but it was the least least complex, but also least accurate. And then how we thought this could be represented in real-world engineering was through global warming. So on the board we have a graph from an article we found about the rising average temperatures around the world from climate.gov. And we thought that through programming we can graph different data points and even predict data points in the future. Like on this graph it goes up to 2100, so we can better combat things like global warming and climate change.
And then the question for electrical engineering was, what graphical application could we build with what we learned?
So on this day, we actually built simulations using 2D and 3D software. This included gravity simulators, solar system simulations, and collisions. The solar system photo here is actually from a program that we created that would take an actual amount, like 365 days, for it to completely revolve around the sun. And then the second image is from a collision simulator.
And then how can these 2D and 3D models be used in the real world? First of all, they can be used for making engineering schematics, which is companies like NASA, tech companies, manufacturing companies. Almost every industry that you can think of uses 3D models to create products. It's the standard in industry. They allow you to see how different parts interact, which you can't do on paper. They're also cheaper, they're more accurate. They're basically just a completely more superior way of drawing things. And you can also simulate real-world situations on 3D models without spending any money. And we also have a CAD model here that was made by Edward.
Yes, I made this using on chip. It's 3 remodel of my school's sword drive that we used to participate in a robotics competition. On the last day, we learned about mechanical engineering and the prompts. What are the 3 best lessons we learned using our automatas, and how can we use them in the future?
So as you can see there, we created 2 different catapults, which we want to demonstrate right now. But these catapults were originally inspired by Da Vinci's flapping wing with a pivot point which flapped the wing. And we wanted to do something similar to that, but a little bit different. And catapults was the first thing that we thought of that was interesting to us and also utilized that pivot point. Our group actually made 2 catapults, one using an elastic rubber band and one using just your hand force pushing down on a button. And these catapults use principles of engineering such as torque, force, and elastic energy.
And then the 3 lessons that we got from making our catapults was first trial and error, because as you can see, there's a lot of duct tape. We had a lot of problems with durability and creating catapults that we had to, innovate with. It took a lot of tries, but we did finish with a good end product. The next was innovation, because we created 2 different designs to see which one would be more efficient and would launch a marble further, which we were on one of 2 groups that made 2 designs. And then the last was collaboration, because without all 5 of us, we wouldn't have been able to create the designs that we did and made them as good as they were. Thank you.
Are there any questions?